Hi everyone, welcome to my YouTube channel Tutorial on my lecture. Today I want to discuss the analog electronics lecture analog electronics in semiconductor physics part 3. I have already discussed part 1 and part 2. In part 1 and part 2 I have discussed thermal voltage, class, classification of temperature, thermal voltage and relationship between thermal voltage and temperature, band gap, band relationship between band gap and temperature, electric field and mobility, and the relationship between mobility and temperature and the property of germanium silicon and so on. If you not watch that two part yet, this please watch that both part from given link in the I icon. So I start today's video, semiconductor which is part 3. Before starting that today's video, I want to recall the important formula that I have discussed in previous two parts. So let's start. First formula is Pt equal to T divided by 600. It shows the relationship between thermal voltage and the temperature. Here it is thermal voltage and T is temperature. Then the next formula, is Ag3 equal to Ag0 minus beta of T. Here it shows the relationship between different energy gap in different temperature. Here is Tt is temperature in energy gap in T temperature and H0 shows the energy gap in 0 degree Celsius, 0 degree Celsius, 0 Kelvin, and beta is material constant and T is temperature in Kelvin. And the next formula is about mobility of charge carrier. Mobility of charge carrier equal to Pt by E. Here E is field and V is drift velocity and mu is mobility of charge carrier. And the next formula is showing the relationship between mu and the mu means mobility and temperature. It is mu equal to T to the power minus m. Here T is temperature in Kelvin, mu is the mobility, and the m is material constant. And next you have to remember and magnitude. The ratio of the mu n and mu p, ratio of mu n means mobility of electron divided by mobility of hole is equal to 2.1 for germanium and and 2.6 for silicon. Mm, all this equation is important for your exam point of view. You have to remember this magnitude also. mu n divided by mu p equal to 2.1 for germanium and 2.6 for silicon. So I like to start today's video. In today's video, I want to discuss the relationship between mobility, mobility and electric field. Electric field, electric field, Vt versus E. Before starting the discussion, I like to plot a graph between mobility and electric bill. So I can plot the graph here. This axis is mobility and sorry. It is mobility versus electric bill. So new here the this axis is mu and in this axis is E. Here the unit of E is volt per second. Okay. In this region, that region, that region, and that region, that region is that region is molar field, molar field, small field. That region is small field. That region is medium field, medium field, and that region is larger field, larger field. So for smaller field, for smaller field, mu is constant, mu is constant, mu is constant. For smaller field, mu is constant, and for medium field, mu equal to 1 by root over of E. Okay, and for larger field, and for larger field, mu equal to 1 by E. For smaller, for smaller field region, smaller field, smaller field, for smaller field, mu is constant, constant, mm, is constant for medium field, field, for medium field, mu equal to 1 by root over of E, and for larger field, larger field, mu equal to 1 by E. Okay. Then I want to discuss that three part by part. Okay. So from here for smaller field, for smaller field, smaller field, for smaller field, for smaller field, You already know that the for smaller field mu is constant, and also we know mu equal to Vt by E. So Vt equal to Vt uh, equal to mu E. So as mu is constant, Vt proportional to A. For molar field, Vt proportional to A. Okay. Next come for medium field. For medium field. For medium field. For medium field. For medium field, mu equal to mu proportional to 1 by root over of E. And we already know Vt equal to mu. No. Here, so we can put the value of mu here. So Vt proportional to 1 by root over of E into E. If I cancel that E from root over of E, so here we get Vt equal to root over E. So for medium field, Vt proportional to root over of E. Then we come for larger field. Larger field. Larger field. For larger field, you already know that mu equal to 1 by E. And we also know it is into mu E. So if I put the value of mu here, it is equal to 1 by E into E. So I cancel that E from that E. That comes it is equal to constant. Okay. If I summarize the above discussion, so we can get for molar field, for molar field, mu equal to constant, and Vt equal to A. Next, for medium field, for medium field, mu proportional to 1 by root over of E, and root over of E. And for larger field, for larger field, mu equal to 1 by E, and Vt Vt is constant. So if I put the relationship, if I put the relation and between Vt versus E in the graph, so we can get this axis. We put Vt and in this axis we put E for smaller field Vt closer to E, and for medium field Vt closer to toward E, then it become constant in larger field. You can understand. If I put this is medium field, this is molar field, up to this is molar field, to this is molar field, up to this is medium field, and above this, after this is larger field. It is small field. This is medium field, and this is larger field, larger field, larger field. So for smaller field in this region, the E increase, the relationship between Vt and E is directly proportional, and in this the relationship between Vt and E is sublinear, and after that region, um, Vt become constant. So we can say Vt become saturate. So the graph enter into saturation region. So if I write in a word, write in sentence, it becomes if if we increase increase E gradually, E gradually gradually, then first first the graph is linear. The graph is linear linear for molar field. Then it is non it is non it is non-linear non-linear for medium field. Medium field. Then then the graph then the graph enter into saturation region. Saturation region for larger field. Larger field. Larger field. Then I want to discuss the Einstein equation. Einstein equation for E Einstein equation in semiconductor. Semiconductor. Einstein equation in semiconductor. It shows the relation between it shows the relation between diffusion constant. I will later discuss the diffusion constant and the drift constant later. Okay. So Einstein equation gives the relationship between diffusion constant and mobility and thermal voltage. Thermal voltage. So if I write this equation in equation, then it becomes diffusion constant D by mobility divided by mobility equal to thermal voltage Vt. Here D is diffusion constant, mu is mobility, and Vt is thermal voltage. If I rewrite this equation for coal and electron, then it becomes Dn divided by mu n equal to dp divided by mu p equal to Vt. Here Dn is diffusion constant, diffusion constant of of electron. dp diffusion constant of whole movement mobility of electron and the mu p mobility of mole or mobility in thermal voltage. So, the relationship between Gn and Gn divided by mu n equal to Gp divided by mu p equal to Vt. It also can be asked in exam. So here we can discuss some unit. The unit of d by mu is volt. Also, the examiner can confuse you by asking mu by d. Mu by d is also volt per inverse. You please check the question carefully. If it is d by mu or mu by d. Okay. So the unit of diffusion constant, unit of d, the unit of d, unit of d, unit of d or diffusion constant, unit of d equal to d equal to mu into Vt as d by mu is equal to Vt. You already know. So d equal to, I write it in next page. Okay. The unit of d. The unit of d. You already know that d by mu equal to Vt. So d equal to mu and Vt. You know the unit of mu is meter divided by volt second and Vt is volt. So if I cancel this volt from this volt, then it becomes meter per second. Okay, so the unit of d is meter square second or centimeter square per second. Okay. Here one question can be asked. I discuss it. One question can be asked. One question can be asked. If temperature T increase, diffusion diffusion constant constant and become diffusion constant A increase B decrease C remain constant remain constant and and D is none of the above. None of the above. The enthalpy decrease. How it is enthalpy decrease? Let's discuss here in next page. You all know that D equal to enthalpy. You all know that D equal to mu D. Okay, and I have already discussed in previous chapter that mu equal to t to the power minus n. The value of n is 2.5 for electron and 2.7 for hole. Hole, it is 2.5 for electron and 2.5 for electron and 2 for hole, and it is for silicon. About the silicon, and it is 1.66 for electron and 2.33 for hole in germanium. So if I put the value here, in the put that value here, so it becomes so they become proportional to t to the power I let the value is 2.5, and we already know that v proportional to we already know that v proportional to t. The equation of v and vt and t vt t divided by 0 0. So it is t. So remaining become t proportional to t to the power minus 1.5. So the value is decreasing. So what is division? Division constant is decrease equal increase t increase t. Then you have to remember some magnitude about you have to remember some magnitude. Magnitude of the and dp both for silicon and germanium. For silicon it is 34 square per second. The value of dp is 13 square per second. Value is 99 square per second. This is 47 square per second. All value are in all value in room temperature. Room temperature or T equal to 300 K. 300 K. So if someone asks you in germanium, what is the value of dn by dp? In germanium, the value of dn by dp is actually equal to the mu n by mu p. If I and you already know that mu n by mu p is 2.1 for germanium, and in silicon dn by dp equal to mu n by mu p. The value is 2.6. So here I end the lectures today for today. I will be back for 2 minutes. Till then, thank you, thank you all, and and keep preparation. Please, if you like this video, please like, subscribe, and share, because it is only motivation for me. Okay. So again, thank you. Bye. Stay safe till then. Okay.